Every person has a light with him. Every ray of light that is radiated by him makes him shine in the white world. Now, I invite our chairperson, Dr. A. Pandikumar, scientist, SASIR in Central Electrochemical Research Institute at Karaikudi.
So, shall I take over this session?
Yeah. Please take care of this session. Yeah.
Okay.
Please take care of this.
Thank you. It's my privilege to introduce today's speaker, Dr. Venkata Krishnan, from Indian Institute of Technology, Mandi, Himachal Pradesh. Dr. Venkata Krishnan completed his PhD in physical chemistry in the year of 2006 at the University of Stuttgart, Germany. Later, he moved to University of Pennsylvania. From 2006 to 2010, then he moved to Ning's, Japan for his postdoctoral work. Later, he joined as a faculty in Indian Institute of Technology, Mandi, in the year of 2012. His research group is mainly working in the field of green chemistry and heterogeneous catalyst for energy and environmental remediation applications. He also successfully guided 6 PhD students and 16 MSc students to complete their project. Also, right now he is guiding 8 PhD students and 10 MSc students. In addition to this, he is supporting for several short-term internship programs. So that will be useful for budding researchers. He also published more than 130 articles in well-reputed and international journals. And also he served as a reviewer for several scientific journals. He already won the awards like a DST Inspire Faculty Award and the IIT Mandi Foundation Day Award for excellence in research and teaching, as well as Monarch Research Fellowship. This is one of the prestigious fellowship is offered in NIMS. In addition, he got DOE postdoctoral fellowship and DFG doctoral fellowship and DAD visiting research fellowship. Also, such a kind of several awards and fellowship he received. In addition to teaching and research, he has also served IIT Mandi in various administrative positions such as warden of the hostel in main campus, funding coordinator for Advanced Material Research Center, associate dean research. Currently, he is serving as a dean of sponsored research, industrial consultancy and international relations. In addition, he is also serving as a director of IIT Mandi Catalyst, a technology business incubator, and the director of IIT Mandi iHub HCL, a technology innovation hub in human computer interaction area. In other than this, he have more credential and there is no time to express everything here. So in this respect, now I request Dr. Venkata Krishnan to take over this session to deliver the talk in this virtual conference.
Yeah, thanks a lot, Pandikumar. Pandikumar is a very good friend of mine. We know each other for quite long time. Thanks a lot for your very detailed and nice introduction. And I would like to also thank all the organizers for giving me an opportunity to give a presentation in this August forum. Let me share my screen and then I'll get started. Is my screen visible?
Yes.
Okay.
Now it is in presentation mode.
Presentation mode. Okay, perfect. Great. Let me open the pointer as well. Yeah. Good afternoon, everyone. So today I would like to talk to you all about the strategic design development of nanostructured heterogeneous catalysts for clean energy and environmental applications. And this is my research group. This photograph was taken in last October. So this is my current research group. This was the first group photograph that we have taken perhaps after this COVID time. Basically, our research group is focusing in the area of nanostructured heterogeneous catalysts, wherein we design and develop different type of nanostructured heterogeneous catalysts, ranging from two-dimensional materials to nice three-dimensional material and also porous materials. So we have a wide variety of heterogeneous catalysts. And with regard to the applications, we are focusing on basically energy and environmental application. And within this energy and environmental application, we focus on the photocatalytic water splitting, which is an energy application, photocatalytic pollutants removal, and environmental remediation application, and biomass conversion to valuable products. This is also an energy application. And apart from these conventional applications, our group is also actively working in the field of green catalysis or green chemistry, wherein we develop catalysts for green organic synthesis. And I'll be talking about mainly these four areas today. And beyond this, our group is also actively working in the area of bio-inspired scaffolds for dip catalysis. And we also study different reactions of how the catalyst is in action during the process, that is in situ studies using UV-vis, LCMS, and SCRE spectroscopy. So the first and foremost thing in the area of photocatalysis, we want to utilize the total solar spectrum. So if we see the total solar spectrum, about 5% of the total solar spectrum is in the UV region, which is very less amount, and nearly 43% falls in the visible light region. And beyond that, the highest amount is 52% in the near infrared region. So how best we can harvest the sunlight for different practical applications ranging from water splitting and also pollutant degradation. So how best we can use the total solar energy distribution. That's one of our predominant goals. And then coming on to the first topic, the photocatalytic water splitting. So we have certain design constraints in having a good photocatalyst. So first, we don't want platinum or any other very expensive material. We want a low cost material. We want an earth abundant material, and we also want a non-toxic material to be chosen as the photocatalyst. At the same time, this material should be capable of harvesting either the full or at least the maximum region of the solar spectrum, which is kind of the visible light region and also the UV light region. Can we use this maximum region of the solar spectrum? In this regard, we chose this material zinc oxide, because zinc oxide, it's easily available, non-toxic and low cost, and it has a band gap of about 3.37 electron volts. And hence, this band gap material, it's not an active under the visible light, but there are different strategies that one could adopt in order to make this material more active. And one of the strategy that we adopted is we kind of doped it or made a composite of this zinc oxide with varying amounts of MOS2. MOS2 is another very interesting material which we will be seeing. MOS2 is this molybdenum disulfide, and then another is reduced graphene oxide, in order to form a ternary semiconductor heterojunction nanocomposites. Why ternary? Because it has three components: zinc oxide, MOS2, and RGO. Now, why do we need RGO and why do we need MOS2? RGO stands for this reduced graphene oxide. This is very much analogous to graphene, because the graphene is a single layer and it is quite expensive, and also the process to obtain is not so easy. So it's kind of like a poor man's graphene type of a thing is this reduced graphene oxide, which can be easily prepared in the laboratory using this Hummus method, and followed by subsequent reduction strategies. So it is analogous to graphene. It also has a 2D hybridized carbon atoms, and this is also a very good electron conductor, and it also possesses very good electronic, optical, and mechanical properties. And another material which we have used here is this MOS2. MOS2 is this molybdenum disulfide. It is also a two-dimensional material. It has a stacked layered type of a structure, just like a pile of paper. It has just a stacked layered structure. And the beauty of this MOS2 is it has sulfur atoms which are on the exposed edges of MOS2. So these sulfur atoms on the exposed edges, they have a very strong affinity towards the H plus ions in the solution. So they can kind of grab this H plus ions in the solution, and then eventually these H plus ions can be further reduced to H2, which is during the photocatalytic reaction. So that's the reason we are using this MOS2 in this case. Now, after we thought about it and decided that, okay, these three materials are good to make a nanocomposite. Now comes how to make this nanocomposite. So first we started with the graphene oxide, the GO, which is exfoliated from this graphite. and then took this graphene oxide along with the precursors of MOS2, which is this sodium molybdate and also L-cysteine. So we took this precursors along with graphene oxide in a hydrothermal reactor in order to obtain a MOS2 RGO nanosheet. And we prepared this nanosheet in a 1:1 ratio, which means that 50% of this material is MOS2 and 50% is reduced graphene oxide. And if you can imagine that the reduced graphene oxide is formed during this hydrothermal reaction, the graphene oxide gets reduced. And this, you can imagine the reduced graphene oxide as a big carpet type of a material, which kind of covers a bigger two-dimensional plane. And the MOS2, which are shown here as this black things. So this is also a two-dimensional material, but this is a much smaller two-dimensional material. Just you can imagine that the sheets of paper are spread across this big carpet. Carpet is also 2D and the sheets of paper is also 2D. Then subsequently, we took this MOS2 RGO with the precursor of the zinc oxide in varying proportions, which I'll explain, in order to prepare this ternary semiconductor heterojunction, which is this zinc oxide, MOS2 and RGO. And how it happens is, again, we have the same big carpet and on which the sheets of MOS2 are there. And there is a lot of balls, this yellow colored balls, which are the zinc oxide, which are kind of floating around. If someone has a kid, they could immediately correlate how would this situation be. So this type of a material, which we have prepared using a simple hydrothermal process. Then I was telling you about this type of a material is prepared. Then first and foremost, we need to see whether our synthesis is successful. So in order to do that, we did the X-ray diffraction studies, wherein we also prepared a simple controlled ZNO without all this, just a simple zinc oxide, this yellow colored box. And this is the X-ray diffraction pattern of this simple ZNO. And then we prepared this nano composite using this procedure, an in situ procedure, in different compositions ranging from 2 weight percent to 10 weight percent. For example, when we take this 2 weight percent, it means that 98%, the majority is zinc oxide, because this is the active semiconducting material in our case. And then the remaining 2% is distributed between MOS2 and RGO. And then since the composition between MOS2 and RGO is 1:1, which means that there is 1 weight percent of MOS2 and another 1 weight percent of RGO, in this case ZMG2. Whereas when we take this ZMG4, it would be 96% of zinc oxide and 2% of MOS2 and 2% of RGO. Similarly, we prepared the other compositions as well. In all the cases, since the zinc oxide is the predominant material, we could clearly see the X-ray diffraction pattern of zinc oxide. But we cannot see this MOS2 or the RGO presence from the X-ray diffraction pattern, which we observed through the Raman spectroscopy, which I'll show in the subsequent slide. And at 10 weight percent, we start to see a little bit of the MOS2. Because one reason is the peaks of zinc oxide dominate the X-ray diffraction pattern. And the second reason is the MOS2 is found in very, very low concentration. It is in low concentration and also the peaks don't dominate. That's the reason we are unable to see the MOS2 or RGO in this case, but we are able to notice it using other technique. Now comes the morphological investigation. I was telling you about this big sized carpet. It's a 2D material. There are sheets of paper. So how is it actually looking like that? Is this morphology like a two-dimensional? In order to understand that, we did the transmission electron microscopic studies, and those studies are shown here. So the GO exhibits a crumpled sheet type of a structure. It's not a simple, straightforward, nice carpet which you can find in restaurants and hotels, but it is some sort of a carpet which is there in a daycare center where a lot of children play. So it's kind of like crumpled type of a thing. And then we could see in the RGO MOS2 composite, which is this one, you can see that there is a big carpet, which is the RGO, on which the sheets of MOS2 are lying down. And this is the HRTEM image, which is the high resolution transmission electron microscope, which shows the lattice fringes, which could be seen here. And these are the nanospheres of zinc oxide, which is the pure zinc oxide here. And this is for the nano composite. So you can see that the big sheet type of a thing, on which there are certain regions, there are this black colored MOS2, and certain other places you can also see this zinc oxide lying on that. And in the HRTEM image, we can clearly see the interface between that. That's why we are calling this material as a heterojunction, because there is a reduced graphene oxide, and there is also this MOS2, and there is also the zinc oxide, and all these three are kind of touching each other, and they should ideally be touching each other in order for this electron transfer to take place during the photocatalytic process. So we found a heterojunction in this case. And this is the EDAX data, which shows the presence of all the constituent elements. Subsequently, we also did a very detailed XPS analysis in order to understand what is the oxidation state of each of the element present in the nanocomposite, what is the near electronic structure of these materials, and what type of bonding the binding energies these materials have. So in the interest of time, I'm not going much into the details of the XPS analysis, but we did a very detailed XPS analysis in order to understand the structure of this material more in detail. Then we did this Raman spectroscopic analysis, wherein we could clearly see the D and the G bands of the reduced graphene oxide. And when the graphene oxide gets reduced, the ratio between the D and the G bands would change. That is a proof here. And we could also see certain bands corresponding to the MOS2, which indicates that all the three components are present in our material. So this is also a proof for the successful synthesis of the nanocomposite. Now comes the main question, that we prepared this nanocomposite thinking that we want to absorb more of the visible light radiation, or the majority of the sunlight radiation, because zinc oxide has the capability only to absorb the UV radiation, which is from 200 to about 400. You can see that the zinc oxide absorbance is still 400. But when we prepare this nanocomposites in the varying proportion, we can see that slowly we could see that the absorbance in the visible light region also increases. So this is the most important thing for this particular work. We also could see it from the color of the samples as well, because color is a kind of a first indication. It's not the final indication. So like sugar and salt, both are white in color, but they have completely different properties and all. But at least we can get some information from the color of the sample. So the GO and the MOS2 RGO, these are black in color. Zinc oxide is fully white in color, and the different nanocomposites are in different shades of gray color, which you can see it. Then another very important property is the thermal stability of the material. How long is this material thermally stable? And we studied it using the TGA, thermogravimetric analysis, and we found that the samples are stable to a definitely a good temperature. And then after doing this detailed studies, the characterization studies, we subjected this material for the photocatalytic hydrogen evolution. So we used a direct sunlight, and then we used water as a solvent along with certain scavengers, because the scavengers are important, because the hole scavengers will scavenge the holes, and then the electrons are directly involved in this process. Then we did this photocatalytic hydrogen evolution experiments under direct sunlight for all the samples that we have prepared. And to our surprise, we found that for one of the sample, which is the ZMG4 sample, having 4 weight % of MOS2 and RGO, gave the highest amount of hydrogen evolution. And this is very interesting. And the hydrogen evolution is very good, which is about 28.616 millimole per hour per gram, which is a very high value in comparison to several other examples which are reported in literature. So this is something which is very good. And why particularly this ZMG4 sample is giving the best result? That's a question, because we can see from this absorbance data that ZMG4 has also good absorbance in visible light, but the other samples are having even better absorbance in the visible light. So why not the other samples are giving a better result? But here we can see that it is the this ZMG4 sample has an optimal amount of MOS2 and RGO along with zinc oxide. And when we further increase the concentration of MOS2 and RGO in the sample, for example, in the ZMG5, 6, and 10, the sample becomes more and more darker, which means that the active semiconductor is the zinc oxide. So the active semiconductor is covered by this dark colored MOS2 and RGO, and that is not allowing the sunlight to interact with the zinc oxide, the energy levels of the zinc oxide. So that's the reason we could say that ZMG4 gives the best result here. And then now we were a little bit greedy. We thought that, okay, can we increase the amount of the catalyst so that we can increase the amount of hydrogen production? So if we change the amount of catalyst, can we get it? But that's not true. Even we can get very good hydrogen evolution just with 3 milligrams or 5 milligrams. And when we further increase the amount of the catalyst for this reaction, the activity decreases, because this is decreases due to the aggregation of the catalyst. So when the catalyst aggregate, so the effective surface which is exposed to the sunlight gets minimized, and that's the reason it is not so effective. We also did the we also did the recyclability of our catalyst, this ZMG4, and the catalyst is very stable and it could be recycled for 4 times or even beyond. We stopped at 4 recycles. So this shows the heterogeneous and recyclable nature of the catalyst. Then everything is nicely done. Now we wanted to understand what is the mechanism, why this particular material is able to give such a high amount of hydrogen evolution. In order to understand the mechanism, we thought that we will study the catalyst which is recovered after those 4 cycles. So what we did was we took this catalyst after the 4 cycles and then studied its morphology using the SEM and the TEM techniques, and studied its crystal structure using the X-ray diffraction technique, and also this EDAX, so and elemental mapping as well. And to our big surprise, we found that there is zinc sulfide is also formed during the reaction. It could be seen both from the XRD. It's a small amount of zinc sulfide which is being formed, but it is formed during the reaction. And we could also see the corresponding fringes in the high resolution TEM data. And this zinc sulfide is forming because of this scavenger which we are putting, which is the sodium sulfate with sodium sulfide. This particular scavenger has a sulfur, and that kind of reacts with the zinc oxide to form this zinc sulfide in situ. And although this zinc sulfide is formed, it is playing a very positive role in this case, because the number of transfer interfaces gets increased because of the formation of the zinc sulfide. So now we can see zinc sulfide, zinc oxide, MOS2, and RGO. Actually, this ternary nanocomposite, in fact, becomes a kind of like a quaternary nanocomposite during the process, and that that leads to better photogenerated charge carriers, or better separation of the photogenerated charge carriers, leading to the better photocatalytic activity. So we could clearly see that there is a synergistic effect between MOS2 and RGO when it is coupled with zinc oxide, and this leads to better production of hydrogen gas. And this work was done by my PhD student, former PhD student, now is Dr. Sunil Kumar, and this was published in the journal ChemSysChem in the year 2017. Now we thought that, okay, we have this ternary nanocomposite, or in fact a quaternary nanocomposite. Can we do the same thing with just a simple 2-component system, just a binary nanocomposite? So in order to do that, again we took this zinc oxide, and this time we kind of doped this zinc oxide with a nitrogen, so that the valence band position, there is a valence band, there is a conduction band, so the valence band position is slightly modified so that the band gap gets reduced. Then we coupled it with another visible light active semiconductor, which is the graphitic carbon nitride, and then prepared a nanocomposite using these two material, n-doped ZNO and graphitic carbon nitride material. And in this case, both are in 2D form, 2-dimensional form. So they can make a face-to-face contact. The 2D can make a face-to-face contact. So there is a much better possibility for this electron transfer. And then we tried again the same photocatalytic hydrogen evolution. And this work was also done by my student, Dr. Sunil Kumar, and it was published in the year 2018 in an International Journal of Hydrogen Energy. In yet another work, what we did was, we thought it's better to use this molybdenum disulfide, because MOS2 has a lot of exposed sulfur atom, and this exposed sulfur atom has a strong affinity towards hydrogen, H+ ions in the solution. Then we thought, can we purposely introduce more and more of this exposed sulfur atoms? So we created a defect-rich MOS2, which means that there are more dangling sulfur bonds in that MOS2. And then we kind of made a composite of this MOS2, defect-rich MOS2, with zinc oxide nanorods in order to prepare some heterostructures. And then these heterostructures were used for the hydrogen evolution, photocatalytic hydrogen evolution, under direct sunlight radiation. And we did this work, and this gave a much better result. And this work was published in SCS Applied Energy Materials in 2019. And this was also done by my PhD scholar, Dr. Sunil Kumar. Then based on these works which are done on zinc oxide based material, and we also did few more works. I have only presented some representative works here in this talk. Few more works also we did on zinc oxide based material, and by combining all this and the work from other researchers as well, we wrote a review article on the zinc oxide based materials as visible light active photocatalyst for hydrogen energy and also for environmental remediation. And this work was this review article was also written mainly by Dr. Sunil Kumar, and this was published in Catalysis Review in the year 2020. Now we are moving on to another type of a material. So we have been talking about zinc oxide so far, but can we get even more better material or other material here? So we focused on other type of semiconductors as well, wherein we focused on the calcium titanate. So in this calcium titanate, we took also this nitrogen doping onto the calcium titanate to change the band gap by moving the valence band position, and then supported this nitrogen doped calcium titanate on reduced graphene oxide sheets, the RGO sheets. And here the nitrogen doping again narrows down the band gap by increasing the valence band level. And this RGO nanosheet plays a dual role or multiple role it plays. The main role is acting as a support for the absorption of the pollutant. And second, it is also helping in the degradation process, degradation of the pollutant under the visible light radiation. So, and we prepared in this case the end-doped calcium titanate in varying amounts with RGO to prepare this binary nanocomposites. And these material were used as bifunctional photocatalyst. Why bifunctional? First, the absorption process happens and then the degradation happens. So it's a bifunctional photocatalyst for the degradation of a model pollutant. We took methylene blue dye. And we also studied the thiabendazole, which is a colorless pollutant under visible light radiation. And why it is important to study a colorless pollutant? Because we want to ensure that the degradation process is mainly because of our catalyst and not because of the photosensitization property of the dye. And similar to the previous work, we did a detailed characterization of this material using X-ray diffraction, wherein we did for simple calcium titanate, the end-doped calcium titanate, and the end-doped calcium titanate with varying amount of reduced graphene oxide, ranging from 1 weight percent to about 20 weight percent. We also studied the Raman spectroscopic investigations. We also did the TGA, thermogravimetric investigations. Then we did the morphological studies, wherein we found that this end-doped calcium titanate has a brick type of a structure. You can see that small brick-shaped structures, and these bricks are sitting onto this bigger reduced graphene oxide. It's like a big carpet, and you are putting too many bricks onto this carpet. So that type of a structure happens. This is the HRT-EM image. Then we did also a very detailed XPS study in order to understand the oxidation state of each of the element in the sample, then the electronic structure, and what is the interaction between the different elements present in the sample. Subsequent to the detailed characterization, we used this material for the adsorptive photocatalytic degradation of the pollutant. And we used two pollutants. First and foremost is this MB dye, which is a model pollutant. And these are the kinetic data which is obtained using these samples. And you can see that there is a contribution towards the adsorption. And then after adsorption, there is also a degradation. And this sample, NCT20, gave the best result here, both in terms of the rate constant as well as in terms of and another very important thing in the photocatalytic degradation of pollutants is what type of fragments are being formed. Degradation process eventually will lead to complete mineralization, wherein carbon dioxide and water are the only byproducts. But in reality, we get many small byproducts and as an intermittent byproducts, and eventually this may lead to CO2 and water, which will take a much longer process. But what are these byproducts which are being formed, and are these products toxic or non-toxic? We haven't done the toxicity analysis, but at least we could decipher what are the byproducts which are formed by doing a detailed degradation pathway study using HRMS technique or this LC-HRMS technique. Then we could take this MB dye, and then it gets broken down into these are the much smaller fragments which are formed from the MB dye during the photocatalytic degradation. Then based on all these results, we were able to decipher a mechanism for this entire process. And we also studied the stability and the recyclability of the best catalyst. And this work was done by my former PhD scholar, Dr. Ashish Kumar, and it was published in this journal, Material Chemistry Frontiers, in 2017. Then as a follow-up of this work, Ashish also did work on calcium titanate and by coupling it with graphitic carbon nitrate, and we used it for the degradation of a different type of an organic pollutant. And this was published. Yes, any question? Yeah. And this was published in Beilstein Journal of Nanotechnology in 2018. And in yet another work, we thought, can we make the material which is good both for the photocatalytic hydrogen evolution as well as for photocatalytic pollutants removal? So we took this calcium titanate and that to a mesocrystals of calcium titanate. Mesocrystals means they have small crystallites, like small ice cubes, which are kind of kept together, and it's kind of like a mesocrystal type of a material. And then we kind of coupled this mesocrystalline calcium titanate with its sulfur atom enriched, which is the defect rich MOS2, and on reduced graphene oxide. And then we studied its photocatalytic performance, both for hydrogen evolution as well as for the pollutant degradation. And we got very good results. And these results were published in the journal Chem Photochem in 2020. And this was also done by Dr. Ashish Kumar. And based on these works on calcium titanate and few other materials, strontium titanate and other perovskite oxide based materials, we had written a review article. And this review article was published in ACS Catalysis in 2020. And our work was also featured on the front cover of the ACS Catalysis, the September 2020 issue. Now, so far I have been talking about how best we can utilize the UV region and also the visible region of the sunlight. Now we'll see about how we can utilize this NAR region, because the NAR region is 52% of the sunlight, which is a very long region. Can we best utilize this NAR region? And for that, we designed a quaternary photocatalyst, which can not only use the NAR region, but also use a broader region, both visible and NAR region. And in order to make use of this NAR region, we need special type of material. Here we have used this special material as this upconversion nanoparticles. And upconversion nanoparticles are this new generation fluorophores. They are mainly able to convert the near infrared light, NIR light, into visible light. That is, it absorbs the low energy light and emits higher energy light by a nonlinear optical process. So basically, this upconversion nanoparticle consists of some lattice, which is kind of sodium yttrium fluoride lattice. And this lattice is doped with lanthanide ions, like for example, ytterbium and erbium. And by tuning the identity of this lanthanide ions, we can tune the emission wavelength. So what happens is when the NAR photons are falling onto it, 2 or 3 or 4 multiple NAR photons are falling onto the subconversion nanoparticle, and this there's some internal nonlinear optical processes happen, which leads to the emission of a higher energy radiation, which is in the visible light or sometimes even in the UV light. And if we have tuned this identity, for example, if we have ytterbium with erbium, it will be a green light emission. If we have ytterbium with holmium, it will be a red light emission. If you have ytterbium with thulium, it will be a blue light emission or a UV light emission. So we can tune the emission wavelength. So this upconversion process can be contrasted with this conventional luminescence in this way, that in the conventional luminescence, there is an absorption from a lower energy level to a much higher energy level. Then there is a non-radiative decay and followed by an emission, which is from a slightly lower energy level to the lowest energy level. So here, this absorption wavelength is much higher, and absorption energy is much higher than the emission energy. On the other hand, in the upconversion luminescence, there are multiple absorptions which are taking place. So one NIR photon gets absorbed here, another NIR photon gets absorbed here, and the emission happens from the higher energy level to the lowest energy level, which leads to a higher energy in the emission process. So this is the upconversion process. And these upconversion nanoparticles are extensively used in other applications such as this biomedical applications, which includes bioimaging and theranostics because of its unique properties. But we wanted to use it for photocatalytic applications. So their role in photovoltaics and photocatalysis is rather limited, but we wanted to encash this opportunity here. And basically, in this case, the material design, how we did was, we took this upconversion nanoparticle, because when the upconversion nanoparticle, it gets the NIR photon, either from the sunlight or from an NIR source, this will emit visible light photons. Then we took the subconversion nanoparticle having ytterbium and erbium, which will be emitting green light. Then we coated this material with another material which has the capability to absorb the green light emission. So we took this material and coated it with semiconducting material, which is the cadmium sulfide. And cadmium sulfide has a band gap of 2.4 electron volts, which converts into about 540 nanometer, which is about which is in the green light region. So this green light, which is emitted from the subconversion nanomaterial, gets absorbed by the cadmium sulfide. Then we, in order to further enhance it, we decorated this material with gold nanoparticles, because the gold nanoparticle will have the plasmonic enhancement effect. So if when visible light radiation is incident, this will show the plasmonic enhancement. So it will be much better. Then based on our previous experience, we took also this reduced graphene oxide, because the reduced graphene oxide plays multiple roles. It plays as the role of an electron transporter because of its conducting nature. It plays the role of an adsorbent for the pollutant, thereby facilitating this photocatalytic process. So we prepared this quaternary photocatalyst, which consists of the upconversion nanomaterial, then the upconversion nanomaterial with the shell of cadmium sulfide, then with it is decorated with this gold nanoparticles, which are this red dots here, and the entire thing is supported on the reduced graphene oxide. So we prepared this quaternary material. And then we prepared this material in different compositions to prepare a nano composite with 1 weight % RGO to 5 weight % RGO. And similar to the previous work, we wanted to see that how, whether our synthesis is successful and what type of morphology is being formed in this material. So for that, we did the detailed X-ray diffraction characterization, which is shown here in these two slides. And we could clearly see that our material synthesis is successful. Then from this SCM investigations, we were able to see the monodispersity of the particles which are formed. You can see that the particles are almost monodispersed, and this is for the nanocomposite. And further morphological information was obtained from TEM analysis, wherein we could clearly see this core shell type of a structure, wherein the dark colored, the internal region is the core, and the light colored one, which is the cadmium sulfate, is the shell. And this is for the overall nanocomposite. Then we did a very detailed XPS characterization, and from the XPS also we were able to experimentally determine what is the valence band maximum position. So we did this UPS, or the special type of XPS, wherein we could experimentally determine the valence band maximum position. And then we did the normal XPS to understand the oxidation state and the other properties of this material. And since this is an upconversion nanoparticle, we also studied this. It's upconversion luminescence, wherein we could clearly see the green light emission here. There is also a red light emission, but that is suppressed, and green light emission is the predominant thing. And thus we can clearly see even from a visible light naked eye experiment, wherein you take this upconversion nanoparticle, disperse it in a solvent like water, and then you have an NIR laser. Just like this is a red laser, so you have an NIR laser, which we cannot see. You just pass it. Wherever it passes through the sample, you can see a bright green line, which is shown here. It's in a cuvette, and the bright green light shows the upconversion property. Then we, after doing all this characterization, we utilized it for the photocatalytic pollutant removal experiment, wherein we chose a colorless pharmaceutical pollutant, which is the ciprofloxacin drug. And first we did the adsorption studies, how this drug or the pollutant is adsorbing. Adsorbing means it's sitting onto this material. Then we did this adsorption study, and we fitted the adsorption data using Langmuir and Freundlich isotherm, and we found that Langmuir isotherm fits the data better. Then we did this photocatalytic pollutant degradation experiment, and first under the visible light. Visible light because it has cadmium sulfide, which is a visible light active semiconductor. It also has the gold nanoparticle, which has the surface plasmonic resonance effect under the visible light. So visible light, it should work. So we did the visible light experiment, and we found that one of these sample, which is the UCAG4, which is having 4 weight % of the reduced graphene oxide, shows the best result. Then we did the NIR light experiment. So for the NIR light experiment, we used the solar simulator, and we blocked the UV light and the visible light, because we can also do this experiment using direct sunlight, but we need to kind of block the UV and visible light just to ensure that whatever is happening is because of the NIR light. So we blocked this UV and visible light using a thick band pass filter and allowed only the NIR light to penetrate into the sample. And we did this experiment, and we found that the UCAG3 sample here exhibits the best photocatalytic activity. We also did the photoelectrochemical studies, wherein we studied the photocurrent as well as this EAS, the electrochemical impedance data. Then through the Nyquist plot, we also derived an equivalent circuit here. In the interest of time, I'm not going much into the details, but if there are any questions later, I'll be happy to answer them. Then based on all these experiments, we were able to decipher a mechanism for this photocatalytic activity. Basically, if the light is visible from the visible light region, there is no role of upconversion nanoparticle, and it's only the cadmium sulfide and the gold nanoparticles which are playing the role. The visible light is impinging on this material, which leads to the promotion of an electron from the valence band to the conduction band, which leads to the photocatalytic activity. The ciprofloxacin gets degraded into much smaller fragments. On the other hand, when we use the NIR light, so the NIR light has a good penetration power. So it can penetrate through the cadmium sulfide, which is a thin shell, and to reach the upconversion nanoparticle, and that will interact with the subconversion nanoparticle, leading to the emission of a green light, because we have the ytterbium and erbium combination. This emission is shown here as an energy transfer, ET here. And this energy transfer leads to the promotion of an electron in the cadmium sulfide from the valence band to the conduction band, and that does this entire photocatalytic activity. This is the mechanism under the NIR light irradiation. So we also did the total organic carbon content measurement, TOC measurement, and found that as a function of time, the total organic carbon content is decreasing, which means that the carbon is getting converted into much smaller fragments. And similar to the previous work, we also did a detailed degradation pathway analysis, wherein we saw how this ciprofloxacin gets degraded into much smaller fragments. Based on this, we also came up with certain equations to explain the process. This work was also done by one of my former PhD scholar, Dr. Ajay Kumar, and this was published in the ACS Applied Materials and Interfaces, which is in the year 2018. I'm just looking at the time so that I can get an idea. So in the next work, what we did was we prepared a wide spectrum photocatalyst, wherein we can use UV region, visible light region, and also the NIR region, and also with slightly low cost materials. Instead of gold, we went for silver copper bimetallic nanoparticles, which are also plasmonic in nature under the visible light radiation. We went for the TiO2 material, which is a UV active photocatalyst, and then again this upconversion nanophosphor. And in the upconversion nanophosphor, we used a different combination, which is the ytterbium with thulium, which is a UV active material. So we have prepared this wide spectrum photocatalyst. This work was done by Ajay Kumar in with, and I also taking help from another of my PhD scholar, Dr. Kumbam Lingeshwar Reddy, and this was published in the Journal of Hazardous Materials in 2019. And my other PhD student, Dr. Kumbam Lingeshwar Reddy, he was my first PhD scholar. So he did a lot more work on the subconversion nanoparticles and its application for various different fields like biomedicine, etc. And we wrote a review article, and this review got published in the journal Small in 2018. Now shifting gears, now I'm moving more into the how we develop certain catalysts for organic synthesis. So we developed certain highly efficient catalyst, which is a 2D material for organic synthesis, mainly for the synthesis of indole alkaloids in water. So this material consists of the MOS2 and RGO. So similar to the previous approaches, first we need to characterize this material. We did it using X-ray diffraction and the Raman spectroscopic analysis. Then we did it using the morphology using the TEM, which is shown here, the TEM analysis. And also SCM analysis we did to understand the morphology better. And we also did the XPS analysis to know the oxidation state of this different elements present in the material, and also the neighborhood environment and their interactions. Then we used this material as a catalyst, as a green catalyst for this reaction, for the synthesis of bis-indole methanes. So we took this reactants with a certain percentage of this catalyst in water. All reactions were done at room temperature for different intervals of time in order to obtain this bis-indole methanes. And this is the optimization table, and we could see that the MOS2 with RGO in 1:1 composition at 2 hours at room temperature is giving a 97% of yield of this final product. It's a very good thing. And subsequently, we also changed the different substituents in the substrate, which is the reactant, in order to study the substrate scope. And we were able to do these reactions for many different substrates. And this work was done by another of my PhD scholar, Dr. Ashish Baguna. And this work was published in ACS Sustainable Chemistry and Engineering in the year 2017. And this work was also featured on the front cover of the ACS Sustainable Chemistry and Engineering Journal, October issue. Then Ashish also did a few more works on developing different catalysts for the green organic synthesis. So another catalyst was this MOS2 in combination of with graphitic carbon nitrate. So we prepared this catalyst for the sustainable synthesis of C3 functionalized indoles. And this work was published in ChemCat Chem in 2018. And in yet another work, we prepared a metal-free catalyst, which is this ammonia-doped polyaniline coupled with graphitic carbon nitrate for the synthesis of indole-substituted 4H chromines. This was published in ACS Omega in 2018. And then another work, we did the potassium functionalization on graphitic carbon nitrate and supported it on the reduced graphene oxide and used it as a sustainable catalyst for Navier-Stokes condensation reaction. This was also done by my PhD scholar, former PhD scholar, Dr. Ashish Baguna, and it was published in ACS Applied Materials and ACS Applied Nanomaterials in 2018. And last year, in 2020, one of my current PhD scholar, Dr. Priyanka Chaudhary or Miss Priyanka Chaudhary, she did a single material. Instead of having multiple combination of materials, we took a single material, which is the oxidized graphitic carbon nitrate, and used it as a metal-free catalyst for this hydrogen transfer reactions. And this work was published in Green Chemistry in 2020. Now, moving on to the final part of my presentation, wherein I want to give a glimpse about the research work which we are doing on in the field of biomass conversion. So one of the most important reactions in biomass conversion is the conversion of saccharides to biofuel precursors, which is the 5-HMF, 5-hydroxy-methyl-furfural. This 5-HMF can be used for multiple different applications, and one of the application is for the preparation of biofuels. And we studied this reaction in green solvent and using a simple catalyst, a single component catalyst. So we took this graphitic carbon nitrate and functionalized it with sulfonic acid group to prepare sulfonated graphitic carbon nitrate, so that the material has both Bronsted base and Bronsted acid sites. And we used this material for the conversion of saccharides, different saccharides, like from the monosaccharides to the polysaccharides, into a specific and highly selective value-added product, which is this 5-HMF. We used several different green solvents ranging from water, ethanol, isopropyl alcohol, and dimethyl carbonate for this reaction. And the synthesized HMF was converted further into other value-added products such as this 2,5-bis-hydroxy-methylfuran, 5-chloromethylfurfural, and 5-bromomethylfurfural. So first we synthesized this material using a high temperature furnace, and further functionalization was done using chlorosulfonic acid. Then similar to the previous work, we did a detailed material characterization study using X-ray diffraction pattern and also the Raman spectra. And the functionalization, the sulfonyl functionalization was studied using FTAR, and the thermal stability of the material was studied using TGA. Then the morphology of the material was studied using SEM and the TEM techniques, which indicated a sheet type of a morphology. And further additional information was obtained from the elemental mapping method. Then we did a detailed XPS characterization to understand the structure and the interactions better. And we were also able to figure out how much amount of sulfur is present in the sample due to the functionalization. And we deciphered that about 3.27 atomic percentage of sulfur is present in our sample. Then we used this material as a catalyst for this conversion reaction. So starch gets converted to glucose and fructose, which eventually gets converted to 5-HMF. Then we did a detailed optimization studies. We changed the amount of catalyst to determine what amount of catalyst is better, change temperature, time, and also other parameters like with different saccharides to do a much detailed optimization of the process. We found that 10 mg of the catalyst was best among the different amounts chosen. 200 degrees C was the better temperature, and 5 hours was the best time. And we did it for several different saccharides and found that glucose yielded the best result. We also studied with different green solvents ranging from water, ethanol, IPA, and DMC, both for the monosaccharides and also for this polysaccharides. We also studied the recyclability and the stability of the catalyst after recyclability, because we wanted to ensure that whether the sulfonation is still found in the catalyst or not, or is there any leaching of this functionalized sulfonyl group. And we were able to see that the catalyst is very stable. Then we did a detailed green matrix calculation wherein we determined the environmental factor, mass intensity, process mass intensity, solvent intensity, atom economy, reaction mass efficiency, mass productivity, and carbon economy for various different substrates ranging from glucose, fructose, cellobiose, and sucrose. And the obtained 5-HMF was further converted to other valuable product using normal procedures and relatively good yields. And this work was done by my current PhD scholar, Ms. Trapti Chabra, and this was also published in the journal Green Chemistry in 2019. And finally, to summarize, our group is actively working in the area of nanostructured heterogeneous catalysts. And today I was able to give some representative examples of our work from photocatalytic water splitting, photocatalytic pollutants removal, catalyst for green organic synthesis, and finally about the biomass conversion to valuable products. And once again, I would like to thank all members of my research group, my faculty colleagues and staff here at IIT Mandi for their kind support, research collaborators both within and outside of IIT Mandi, and our centralized instrumentation facilities, which is the Advanced Material Research Center for the characterization facilities. And these facilities are also open to everyone from any academic institutions or from industries. If anyone is interested, you may write an email to me. I'll connect you to our office, and our characterization charges are quite competitive compared to the charges available at other institutions. And these are the different funding sources which have sponsored our research work. And finally, thank you all very much. Thank you.
Thank you, Dr. Venkata Krishnan, for the wonderful lecture. Especially in this lecture, you have covered the much needed topic. Actually, the energy and the environmental remediation application by utilizing the nanomaterials such as heterojunction photocatalyst and upper conversion material for harvesting NIR, as well as making utilization of UV and visible light absorption through photocatalyst for degradation of dipollutant, and finally you have end up with biomass conversion as well as some organic transformation that may be we can consider in the industrial point of view for making the intermediate in that industrial process. So it is much needed topic. Especially I also want to add one point. In your first work, you have talked about hydrogen production by photocatalytic method. Actually, the last year during the independence, our Prime Minister announced the National Hydrogen Mission. Since we do not have any hydrogen production technology by utilizing greener method, the existing method that is derived from the fossil fuel. So maybe one of your key idea will open the hydrogen mission. Okay, now the session is open for discussion. Participant you can ask any queries to the expert.
Yeah, thank you very much, Pandit Kumar, for your detailed comments.
Thank you, sir.
Thank you.
Yeah, I have some discussion with Venkata Krishnan.
Sure.
We had a very good lecture from you. Particularly photocatalyst and biomass conversions catalyst in green energy catalyst also. So you have to your group and your students prepared many good catalyst for photo and biomass. For my discussion, which catalyst is more efficient to utilize commercial applications in the environmental aspects?
Yeah, that's a very good question. In fact, in our design principles itself, we kind of embed that the catalyst should be environment friendly and also it should be low cost in nature. So the first work which I discussed, the zinc oxide with the MOS2 and RGO, this could be one of the good catalyst if someone wants to take it up for commercialization. And further, we could fine tune that catalyst much more nicely in some of our subsequent works, which we have fine-tuned with defect rich MOS2 instead of a normal MOS2, and also the zinc oxide instead of balls we could have some flat two-dimensional type of structures. So we can even further fine-tune those catalysts if we want to take it to the industry. The scaling up will not be a problem because industry main thing they feel is the scale up. Scale up will not be a problem, and recyclability will also not be a problem. Even if we have a limited amount of catalyst that could be utilized multiple cycles. So that could be one of the potential catalysts which could be taken up for commercialization. And there may be many other catalysts. Several researchers around the world and also lot of researchers in India are also working in similar topics. So they may also have some of their best catalysts which could be taken up for commercialization. And as Pandikumar mentioned, that the National Hydrogen Mission should kind of come up with some strategies of good to integrate some of the best catalyst in one reactor so that the amount of hydrogen production is increased. And also more than the amount of hydrogen production, another very important parameter is the STH, the solar to hydrogen conversion. And the STH conversion currently the efficiency is rather very low or very poor. So that efficiency need to be increased. So that is more than the amount, it is the conversion efficiency. STH efficiency is playing a more critical role before the photocatalyst could be commercialized or for industrial use. There is a lot of work which is being done in the electrocatalysis area, HER and all. But for photocatalysis, this STH is currently the big bottleneck. And hardly getting a 1 or 2% of STH will not suffice. At least there should be a 10% STH if you want to take it up further. So these
Okay,
are my
okay,
thoughts.
okay. Okay, it is okay. I have another one discussion.
Sure.
We prepared not only in India, so overall scientists on catalysis work, they prepared so efficient catalyst. But in most of the papers, they won't check toxicity of the catalyst because maybe we have to use many catalysis in solar conversion or biomass conversion, so on and so on. But maybe after 100 years or after 200 years, maybe these all catalysis may be affected the environment. So we also need to consider toxicity of the catalyst. That is very. This is my opinion. That is also very important for catalytic society. Yeah, please share with your
Sure.
thoughts, please.
Sure. Definitely. Yeah. More than a question, this is more of a thought for all the people working in this area. So, in my opinion, there should be some proper standards that need to be developed to test this toxicity of the material. So currently there are not very clear standards or the limits which exist. And some of the people who are in Japan during the time of the earthquake and the tsunami disaster, they were changing the standards of the radiation level rather than kind of keeping it okay, we're strictly following one single standard. And similarly, in many other cases, even in India and all, even for this blood sugar level monitoring, the standards keep changing by the doctors and the associations. So proper standards needs to be developed to test the toxicity, and also proper procedures need to be developed. Currently, the kind of the people who are working on photocatalysis, their method of testing the toxicity is either they give the photocatalytically treated water for the fishes to and see if the fishes survive for 1 week or 10 days or something, or they give it to some plants and see if the plant is sprouting and growing or the plant dies off because of the pollutant. So these are okay, but there should be more control and proper standards and proper procedures need to be developed for toxicity testing. So that I feel is more important, procedures and standards. Then we can come to some consensus in this topic. Yes.
Yeah. Thank you so much for your
Yeah.
good deep discussions with me. Yeah, please.
Yeah.
Thank you.
Thank
Thank
you.
you. Thank
Thank
you.
you.
I think one more participant is asking
Yeah.
question. Preeti.
Dr. Preeti Ravichandran.
Yes, sir. Good evening, sir. Thanks for
Yeah.
such a wonderful presentation. I have a great doubt because I'm also working in a composite material. So, which
Okay.
is the potential candidate to develop a composite, sir? Whether it is a graphene oxide or in the reduced graphene oxide form, which is more potential as a photocatalyst?
Yeah, catalyst, reduced graphene oxide has its own advantages, and graphene oxide, on the other hand, may have other advantages. So the reduced graphene oxide depends on the property, what property you want. So for the reduced graphene oxide, it has this conducting nature because of the reduction of this thing, and there is this carbon structures wherein the conjugated double bonds conduct the electrons. So reduced graphene oxide is more preferable candidate. It's a replacement for the graphene. On the other hand, graphene oxide may have different other properties, insulating properties. So it all depends on what property you want to explore. Then one can come to which one is better. But most of the works on photocatalysis, wherein the electron conduction is playing a very important role, and also in electrocatalysis, reduced graphene oxide is more preferred compared to simple graphene oxide.
Thank you, sir.
Welcome.
Any other queries from the participants? If there is no query, let me thank the speaker for delivering. Yes, anyone?
Nowadays, the people are started with the metals, the combination of the metals to see the various type of inorganic materials.
Can you speak a bit louder, please? I'm unable to hear it very clearly.
Yes,
Yeah.
Or else you can post your question in the chat box. Post your question in the chat box.
So in the inorganic materials, the people are started with more than one metal. Say for example, TiO2 means more than the one metal. They are taking the four metals or multi metals. They are taking, especially in the perovskite material. In
Yes.
that they are taking the multi-component system. So that they are calling it as a multi-component oxides. Right? So
Yeah.
high entropy oxides playing a role right now. So how far these materials will make an impact in future? I need to know about the future trends about that. That's
Future trends. Exactly. That's a very good good question. Instead of a single metal, now the trend is moving on to the multi metal, including the high entropy system and high entropy oxides. But my knowledge about the high entropy oxides is rather limited, so I will not much comment on the high entropy oxides. But definitely in the field of photocatalysis, the trend is moving towards multi-metallic systems. Like even in our work, we have used calcium titanate. In yet another work which I didn't discuss today, there we have used rhodium doped strontium titanate. So there is rhodium, there is strontium, there is titanium. Three elements are present. And also in some of the works from Professor Kudo and Professor Doman, from both from Japan in different institutions. So they have done a lot of work on multi-doped metallic system, multi-metallic system, and have shown very good performance. So the trend is moving in that direction, but it's not so easy to control the stoichiometry. It's not so easy to ensure the phase purity of the material. So it comes with its own set of drawbacks. But definitely, people are doing a lot of research in this area. But how far it will all be successful and can we reach a commercial product? that is to be thought about. Only the future can tell us the answer.
Definitely.
Yeah.
So that domain papers are more related to water splitting, I think.
Exactly. Yeah.
So that only I am interested to ask about the upgrades, whether it may be a boom or not. So people have started, it is more than 2 and 3. So they are saying about the thermodynamic nature of the concerned material. So that I ask. Thank you for accepting and thank you for interested to combine with us. Sir. Thank you.
Yeah, it's my pleasure. It's definitely my pleasure. Thanks for your question.
I think, particularly, we can conclude this session.
Okay. If there is no question, let me thank the speaker for delivering the wonderful lecture in the area of energy environment by utilizing the heterogeneous photocatalyst material. That is much needed topic for the current scenario. He had delivered on the right time. So I would like to thank the speaker for providing the wonderful and valuable lecture. Thank you. Thank you very much.
Thank you, Dr. Pandikumar, and thanks once again to the organizer. And thanks to
Thank you so much for Venkata Krishnan and Pandikumar. Yeah, thank you so much.
Thank you.
Yeah.